P Mathews from the design software company Autodesk. Now, when you think of the grand challenges that are facing the world today, the rising cost of energy, the poor living conditions that most of the world experiences, our aging infrastructure or climate change, these are all design challenges. And you are all designers. You are more important to the world than ever before in history. Now, technology can help. And I'm really excited because I've seen over my career a new technology shift happen about once every decade. But right now, we are seeing a wave of multiple technology shifts all happening at the same time. And they're going to redefine the design industry as we know it. So why do you care? Why does this matter? It's really about business strategy. If you think of any new technology, it often goes through this curve of starting out as impossible, it becomes invented but impractical. Through innovation, it becomes practical and useful, and then eventually customers start to expect it, and then the market will require it. Now, your competitors will often follow this adoption curve of a new technology, the ROI curve, which is that you start to implement a new technology when customers start expecting it or when it's required. But is that where maximum strategic benefit is gained? No. Really, this green curve shows that. This is showing the difference between when something becomes productive and possible, and yet before customers expect it, before your competitors have started to adopt that new technology. And really, if you think about it, if you want to maximize strategic value or separation, you have to invest in and experiment with the technology while it's still in the impractical phase so that you're ready to ride the wave, so that you can do something that your competitors can't or won't do. Rip, mix, burn. It changed the music industry forever. Think of iTunes or Pandora and Spotify. These companies rode a technology shift to really redefine a very old industry. If you think of the design industry, I call it rip, mod, and fab. The CAD industry has really focused on modeling reality for the past 30 years. But this new set of technologies that are coming are going to allow us to rip, mod, and fab atoms the same way that we've done with music. So let's start off with the first, rip. Insiders call this reality capture. If you take reality, it's complicated. Imagine you want to put a new fiber optic cable under this overpass. You have to make a plan. You have to coordinate a team of people to make that change. You need to capture reality. Now, even the most productive software products in the design space all start out this way, the blank screen. And so to gather that complexity is a big problem. It's a hurdle to using this design technology. Amory Lovins at the Rocky Mountain Institute wanted to make the Empire State Building more sustainable. It took him 9 months to capture the as-built model before he could do his first computer simulation. Then along comes this device. This is a $120,000 laser scanner from a few years ago. It can capture reality, millions of points in just a few minutes. A really big innovation. But very few companies use this, only some of the largest. Now, in the last 2 years, we've seen the price drop from $120K down to a little bit more than $30K. And it's become smaller and more accurate with better range. Amazing technology shift. And we're starting to see this technology become practical, where more and more people are using it on not just at the beginning and end of a job, but throughout the entire process. What it results with is a point cloud of three-dimensional locations. And we're designing software technology to take that point cloud and turn it into a model. For instance, scan to BIM, scan into a building model, or into a part model for manufacturing. This is the way a point cloud used to look just a few years ago. You couldn't tell if this point here is the column or the wall behind it. It was hard to visualize. But the technology has been advancing so rapidly, we can do this now. We can experience millions of points as if they're surfaces. We can convert them into models very easily, rapidly accelerating the process. Every text tag you see here is a different laser scan from a different vantage point. And you're interactively moving through huge amounts of data. This is billions of points. They can't fit in your computer's memory. They are being real-time accessed and streamed to your display as an interactive model, down to centimeter accuracy. Imagine entire cities at this level of detail. One of the things we did was not just capture the geometry of an object. This is an office building that we have up in Toronto, and we laser scanned it here. But rather than just capturing the geometry of the building, we also put other types of ripping devices. We ripped the temperature, the humidity, the motion, the amount of electricity used at every single outlet and every desk in this entire office. We hooked it into the HVAC system, measuring all of the pumps and valves in the entire building. It's a living building, and we're capturing all of that. What that allows us to do when we've ripped it is we can model it and do simulations and see how the air conditioning system is really behaving to make for a more sustainable design in the future. Now, this is a device that can be used by manufacturers. It is a chip that you can plug all sorts of sensors in. It wirelessly transmits data, and it generates its own electricity parasitically through vibrations. So as a machine is doing its operation, it can power this chip without any wires, and it transmits that data. There are people taking these chips, pouring them into concrete. So the next bridge you drive over may be a ripping device, or the next foundation in a building is literally alive with information. This ability to rip analog data and bring it into the digital world extends even to brainwave technology. This, from a Motive company, is making a game device that in the future may hook up to your future video game console and read your brainwaves to control the game. This is a product that's already here today. Other ways that we can rip reality are things like this. This BRDF material scanner allows us to take a square centimeter of material and look at how light interacts with a piece of wood or ceramic or glass. And in the movie industry or special effects industry, it uses that data. 1 square centimeter is about a terabyte of information of how light interacts with the material. Which of these two pictures is computer generated, and which is the real kitchen? The real kitchen is the one on the left. Now, we're seeing this convergence of different RIP technologies from different industries. Things from the media and entertainment industry, things from the manufacturing or the building industry. The lines are starting to blur between them. We're seeing a convergence. In the movie Tron, you take this actor, Jeff Bridges, who's aged a bit, and we made him 30 years younger. How was that done? That was another form of reality capture. This monstrous multi-million-dollar device with zillions of cameras and light sources with polarized light can capture you. That's me inside there. It's 4 times brighter than the sun, and you have to not squint while the actor gets their shot done. If you watch The Avengers or Tron, this is another form of reality capture, capturing motion in addition to geometry and material information. That technology has been democratized down to $100. The Kinect was the most successful consumer product device in history in its first 6 months. Now, we have taken at Autodesk this ability to capture reality down to the free price point. What you're seeing here are the Bamyan Buddhas that are in Afghanistan. The Taliban blew them up about a decade ago, totally destroying these magnificent structures. Notice that all of these historic photographs, some taken in the 70s, they all were taken by different people on different days with different cloud cover, different shadows at different times. We send it to the cloud, and it solves for where all of the cameras' positions were. And so what you see here is the ability, just through photographs, to create a 3-dimensional model of that structure. You can't laser scan them, but through photogrammetry technology, we can bring the Bamyan Buddhas back to life. We can take pictures of your foot and have custom-built shoes just for you that have perfect fit. Or take some tourist photos of Notre Dame Cathedral and bring it home with you. The next step in this evolution is really using something that the military has had, which is drones. This is a self-flying drone. You can give it a mission, and instead of carrying a bomb payload, it can carry a 5-pound camera with a nice zoom lens. And here you see us flying over a winery in Napa, capturing multiple pictures, and we're creating a 3-dimensional model. Imagine being able to digitize an entire city in an automated fashion. Now that technology is also being democratized down to a reasonable price point. At the San Francisco airport, I saw this in the gift shop for $300. Notice that it has a camera in the front, exactly what you need to create a 3-dimensional model. So with all of this reality capture, the result is massive amounts of data. This is the kind of data that is in a CAD model for just a single wing of a single hospital in San Francisco. Imagine taking that BIM model, not just for one building, but for an entire city. And that's why things like drone capture and laser scanning and photogrammetry are all really coming together. We now have the technology to have these massive data sets, and that's where the cloud comes in. Because instead of just working with these big files locally on your laptop, they're not going to fit. We're going to have what my friend Doug Eberhard calls BAM models, or big-ass models such as this, where everything is alive. You can go into the basement of the building and see the part number on the pump, on the water chiller. How are we going to do that? Well, instead of moving data files between the different designers on the team and having data move to the people, we're going to have to move people to the data, centralizing data in the cloud, on the internet, on servers, and accessing it remotely through things like iPads or your computer. To do that, we do it much in the same way that you can watch movies over the internet. Netflix, for example. Those systems have had a problem if they've had too much latency. They're too slow. But we have new technology that can allow us to remote video from a program running on a server in under 10 milliseconds. That's less than the refresh time of one frame of animation on your monitor. Now that we've captured all of that reality, the next step is we need to model all of that stuff. And the cloud is really important with that. Now, I think of this as what I call infinite computing. Let's take a sidestep. Let's talk cars for a second. If you take a Toyota Camry, it has performance X. It does 0 to 60 in that amount of time. And it costs you Y dollars. Now, if you have a Lamborghini, it costs a lot more than 2X, right? But it only has twice the performance. So twice the performance, but 4 times the cost. It's an exponential cost curve. And the funny thing is that's true of computers. Whether you have a laptop or a high-end workstation, price goes up exponentially. Or perfume, or anything really follows this price curve. But unlike any other industry, computing industry goes through what's called Moore's Law. The price of computing goes down by half every 18 months. Okay? So for the same $1,000 computer, 18 months from now, we'll get a computer with twice the performance every 18 months. This curve has really shaped the software industry. It's what allows us to do video games, where just a few years ago, we were looking at 2D graphics. The cloud, however, is linear. Think about it. I can rent one computer in the cloud for an hour for $1 an hour. Or I can rent 2 computers in the cloud for an hour for $2 an hour. I can get twice the compute performance for twice the cost. It's a linear cost curve. We've never had that in the entire 30 years of design software. And what that means is that we shouldn't be using design software for these curves anymore. We should be thinking of the fact that our $1,000 buys us compute power over here. And so when you can afford to have a Lamborghini for the same price as the Camry, are you going to drive different? Put another way, I can have one computer do a 10,000-second simulation or visualization or analysis, cost me 16 cents, or I can get 10,000 computers in the cloud, rent them for 1 second, and it costs me 16 cents. So what are we going to do differently with that? Well, one thing is we can actually have computers do design for the first time in history. Here, instead of doing one simulation that might take 12 hours to run to lightweight a part for an aircraft door latch, we can run hundreds of them. Different thicknesses, different widths. We want to lightweight the part to save on fuel, but we want it to be strong enough so it doesn't fail. And the computer can do all of these design variations in parallel on multiple computers in the cloud that I rent. In fact, this researcher did this with buildings, ran thousands of different building simulations in parallel, literally having 2 buildings do what's called computational evolution. Think of buildings having sex, exchanging their genes, their DNA. The DNA could be the size of their windows, how much insulation they have, how they're rotated relative to the sun. Do they have solar panels or not? Those are the genes. The buildings go through a simulation to see how successful they are. The buildings that are most successful are allowed to procreate, have children. You throw in mutations from a product catalog, swap out an Anderson window with the Pella window, and you run another set of simulations on thousands of computers. This researcher ran 25,000 simulations and ran evolution. And what popped out was not something where the human designed the shape. The human came up with the dream, the parameters, the constraints. And it evolved to something that looks like art, or it looks like something nature would produce, biomimetic. Now, we're seeing this computational evolution happen not just on physical products and buildings, but also on virtual bacteria making virtual materials, running virtual software in their DNA, and going through evolution. This is the ability to make new types of materials that combine things like the properties of a rubber with the properties of a brick. Imagine being able to bring those together in an organic way that doesn't have any toxic effects. We can also use this infinite computing to do all sorts of amazing simulation and analysis. Here you're seeing computational fluid dynamics happen in real time. Some of this technology was borrowed from the video game industry, where a traditional CFD simulation might take 12 hours or even a month, depending on what you're asking. But the ability to do real-time rendering using the cloud, real-time simulation, and real-time editing is really going to change about how we think, and not doing analysis after the design, but do analysis during design. And in this case, a simulation using, again, the power of infinite computing to put together this visualization and simulation of an earthquake up in Seattle. Originally, the city wouldn't fund the replacement of the structure. A simulation was done by Parsons Brinckerhoff. Of course, a year later, it was funded on the ballot, and it's under construction now. But after we've ripped reality, we've modified it and modeled it in infinite computing and worked on the data, our next step is to really bring it back to the analog world, fab, to burn it back into the reality that we live in. One way to do that is through rendering. Now, which of these two images is real and which is computer generated? It's a trick question. These are both fake. The one on the left can be generated at 30 frames a second in real time, including all of the reflections in the headlights there. And on the one on the right takes, a couple of hours to render on a normal machine. But another way to bring the digital world into the analog world is through manufacturing. And of course, we've had robotic manufacturing for many years. That led to subtractive manufacturing, CNC milling machines, and so on. But there's this new exciting set of disruptions that are happening in additive manufacturing, or what we call 3D printing. This is a laser cutter, for example. It's another form of computerized manufacturing. The cost of these devices just a few years ago would be in the $250,000 range, and now you can afford one for about the price of a fancy television set. You could take these digital models today and with additive manufacturing, literally print them out in 3D. They come out of the printer already assembled. And the price point of these 3D printers has gone in the last 10 years from about $250,000 down to about $1,000 today. And what's really cool is, what's the first thing you would print on a 3D printer? Another 3D printer. There are over 50 different materials that we can print today. Everything from glass to ceramics to plastics to even biosemiconductors, which is pretty interesting. You're not going to wait in line for your next iPhone at the Apple Store in the future. You're going to print it at home. So what can you print? You can print clothes today. You can print food. You can print a car. This is Irby. You can even print the Earth with land XML files, a differential GPS, some laser sightings, and an Earth mover. You can literally take your CAD model and print the surface of the Earth, just as Disney does with their theme parks. Professor Koshnevis here has printed three-dimensional buildings. The idea is NASA wants to have robots print buildings on Mars before the astronauts arrive. And here is his grad student standing in the lab against a real wall that has been 3D printed by this machine here. It puts things similar to carbon fiber right into the concrete and extrudes it at building scale. And at the Olympics, the last round of runners were all wearing these Flyknit shoes. Nike spent the past 4 years working on this technology to 3D weave yarn into a shoe. So we can rip your foot. We can modify that model based on your performance characteristics of how you toe in during your run and custom build a shoe that is ultra light. Now this is an artist's rendition of something that is actually real. 3D printing organs. When I was at the TED conference, I got to see a couple of doctors who 3D printed both a bladder and a kidney. And it was a living kidney made out of stem cells, and they could be your stem cells. So there's no organ rejection when you have to transplant one. It's you, it's your cells. It's sputtered out onto a calcium lattice, you put it into some food, those cells grow and multiply, they eat away at the lattice, leaving the organ ready for transplant. This is here today. And the Weiss Institute has been doing this research to design self-assembling DNA. By putting the right charges on the DNA, it isn't an instruction set for a cell, but just DNA by itself, that when you put it into water, those charges make it fold, and it folds into essentially a robot. The robot is a box that holds a payload, and it has a lock and a lid. You inject it into your body, it bounces around. When it hits a cancer cell, it binds, it releases the lock, and it delivers the payload. Imagine being able to cure cancer with no side effects more than the common cold. Another way to take the digital world into reality is through augmented reality. Taking a digital model of something, taking some live video and some sensor data, and combining these together. This is an example of seeing, the ultimate stud finder in a wall, or being able to see the pipes that are under the ground, the ultimate call before you dig. So this is all coming. So in summary, we're seeing these wave of technologies that are going to allow us to rip, mod, and fab the atoms of our world, dramatically change how we do design through infinite computing. And I'd like to share with you a personal example that really excited me of something I got to experience at the TED conference, which was riding in a device that combines all of these different technologies, the going from analog to digital, the leveraging of cloud data, the use of infinite computing, the ability to visualize, simulate, and analyze, and then ultimately taking that digital reality back into the analog world. And that is the Google self-driving car.
I am gonna have my hand near the steering wheel, foot over the brake, but I shouldn't. You get to hold the keyboard, so don't.
50 miles an hour heading for a cement wall with nobody holding onto the wheel. This car goes to work every day, and the owner of it says that when he's on the Dumbarton Bridge in stop-and-go traffic, he reads magazines. It's gone on a 600-mile trip up the California coast, gone over the Golden Gate Bridge, picked a lane. It stops at stoplights, waits for old ladies to cross the road, and the driver only had to touch the wheel 4 times in 600 miles. Pretty amazing. So in summary, if you think of new technologies and this wave of changes that are happening, how do you get strategic benefit from it? Now, there are many ways to have strategy for your company. You can excel on price, you can excel on quality, you can excel on speed, or on service. But technology is one other way that you can excel. And so the question for you is, where are you on this curve? Where do you want to be? And how can Autodesk help you? Thank you.